Hi, my name is Alakuijala. In this work, we propose Video Language Critic, a transferable reward model for language-conditioned robotic tasks. We consider the problem of vision-language control, in which the task is described in natural language, such as cross the white object or rotate the dial clockwise, and observations are stacks of past images, or equivalently, videos. Much of the prior work in this setting has proposed to learn language-conditioned policies, which directly predict actions in the target robot's action space, given the image observations and task description. We instead propose to learn a language-conditioned reward function, which predicts a scalar similarity score between the video and task description. This problem is less explored than that of training end-to-end vision language action models, and allows us to separate the concerns of what to do from how to do it. Learning what to do first allows us to use a wider and more scalable range of data sources that do not depend on a given embodiment or action space. Having access to a learned reward model also allows the policy to improve our existing demonstration data by maximizing similarity, allowing the policy to discover better or faster solutions through experience. Our approach consists of two stages. First, we train a reward function on video-text pairs. The reward model is then frozen and used to inform policy training in a new environment. We design Video Language Critic to meet two criteria. First, reward predictions should be accurate, meaning that they should clearly differentiate between successes and failures. Moreover, rewards should be smooth over time. They should capture task progress as early as possible. We start from pre-trained image-level clip encoders, which we fine-tune for video data. The task caption is passed through the transformer text encoder, and each video frame is separately processed by the vision transformer-based visual encoder. Video Language Critic is trained using a two-part objective. To boost discrimination between successes and failures, we use CLIP's symmetric cross-entropy loss. This objective produces high similarity predictions for matching video caption pairs and low similarities for mismatching pairs. To encourage smoothness over time, we add a novel sequence ranking loss to this contrastive objective, which favors monotonically increasing rewards over the duration of a successful video. Specifically, for any consecutive time steps, predicting a higher reward for the earlier steps than the latter incurs a penalty equal to the absolute error of their difference. This allows VLC to learn from all intermediate states rather than only the final states, fully making use of the temporal information in video data. Moreover, we also need to define how to aggregate features over the time dimension. One option explored in previous works is simply taking the average of the image features, but this is not sufficient for reward modeling, as we need to preserve their order information. Most prior reward models have considered the input frames as an ordered sequence, but defined architectures that produce a single visual embedding representing the video as a whole, which is compared with the caption embedding through a distance metric like cosine or Euclidean distance. However, we find that embedding the text and visual modalities separately causes the resulting representations to lose a lot of information relevant for evaluating task progress. Such models are forced to decide which information to keep from the video before they have even seen the task description. We instead propose a temporal aggregation transformer, which takes both the caption embedding and the sequence of image-level embeddings as input and directly outputs a similarity score, maintaining higher representation capacity. We train the aggregator from scratch and fine-tune the text and visual encoders. We also obtain better performance by ensuring that the negatives used in contrastive learning are sufficiently difficult. For videos demonstrating diverse tasks, it is often possible to guess which task is being solved based simply on the objects in the scene. We therefore propose to include failure videos as additional negatives. We leave these videos uncaptioned and treat them only as additional negatives in the cross-entropy loss, while leaving them out in the sequence ranking loss. Prior works proposing to learn language-conditioned reward functions for robotics have considered a variety of objectives, but ours is the first work to use a sequence ranking loss, which fully leverages temporal information, as well as the prior that later states in a video should score higher than earlier ones. Most prior works were also conditioned on just 1 or 2 frames of execution history, limiting the model's awareness of temporal dynamics and excluding tasks with partial observability. Moreover, the majority of prior works propose to separately embed text and visual modalities, with reward defined through cosine, or Euclidean distance, whereas our model benefits from the full expressiveness of the proposed temporal transformer architecture. We will consider these 5 prior works as baselines in our experiments. However, as the original Laurel work used a much smaller architecture and no visual pre-training, we instead consider a re-implementation of Laurel with our architecture and clip pre-training for a fairer comparison, while maintaining its binary classification objective and 2-frame conditioning. We evaluate our reward models based on how effectively they inform successful policy optimization. The learned similarity scores can provide reward shaping for a variety of policy training methods: online, model-based or offline RL, or planning approaches such as model predictive control. In this work, we used model-free RL, specifically soft actor critic. As we focus on the problem of reward modeling in this work, we train separate policies per task, whereas our reward model is shared across all tasks. All reward models are conditioned on images only. To reduce computational costs, however, we consider the low-dimensional state exposed by our evaluation environments as inputs to the policy in this work, but image-based inputs could equally be considered. We apply a few normalization steps to reward model outputs. Values are shifted such that the first reward prediction of each episode is equal to 0, as future behavior should be evaluated relative to this initial state. We also normalize the scale of the rewards according to a common strategy from the RL literature, which ensures that the exponential moving average of rewards has fixed variance 1 minus gamma squared, where gamma is the discount factor of the MDP. Finally, we consider the setting where a sparse reward can be defined, but demonstrate accelerated training through the addition of dense learned rewards. Both components must be weighted appropriately. In particular, once the sparse success signal is obtained, it should outweigh the dense component. We set these weights empirically to 1 and 50, respectively, but did not find the performance to be sensitive to this choice. We evaluate our reward models on simulated manipulation tasks. First, we test in-domain task generalization by training on 40 tasks from the MetaWorld benchmark and testing on 6 unseen tasks. We collect 40 demonstrations and 30 failure episodes per task. We find VLC to outperform all 5 baselines across the 6 held-out tasks, as shown in the success rate curves plotted over the training duration. We group the tasks into easy and hard sets according to how long policy training with MetaWorld's hand design reward, which is based on the full simulator state, needs to solve the tasks. In the table, the success rates are sampled at the training length at which the hand design reward solves the task, to obtain a single number summarizing the curves. We also find that none of the reward models are able to successfully solve the tasks without the inclusion of the sparse reward. On qualitative inspection of the predicted rewards, we find VLC to produce more accurate and smoother predictions than either RoboClip or Laurel, the 2 strongest baselines. Predictions for an example success episode are shown on the top row, and those for a failure episode are shown on the bottom. For successes, the curves should increase consistently over time and end at higher values than for the bottom row episodes. These videos show VLC predictions overlaid with example policy rollouts. Overall, the predicted reward clearly starts to increase much earlier than the button pressing task is solved, have good agreement with the ground truth success signal in green, but show some bias against staying still after task completion, likely due to the success demonstrations ending as soon as success is reached. We also evaluate VLC's ability to generalize to unseen embodiments by training it on data from various robots and tasks from OpenX embodiment, and evaluate on MetaWorld tasks. Of course, this setting is much harder, but our model still achieves an 11 percentage point gain on the hard task set, and +7 on average across all tasks. In individual tasks, there is as much as a 7-time sample efficiency improvement compared to the sparse reward only, although there are also some tasks which are misrepresented, such as plate slide side. VLC can also be treated as a learned state value function, which can score any future state. As such, it interfaces well with model-based methods. In this proof of concept experiment, we do not learn a model, but assume access to a known model, as well as action primitives, namely reaching and grasping and detected objects in the scene. In this setting, The reward model's task remains to identify the video correctly executing the task out of a set of 6 sample trajectories. We find VLC to also outperform RoboClip and Laurel in this setting on held-out meta-world tasks. To conclude, the combined cross-entropy and novel sequence ranking objective, expressive architecture, as well as full video conditioning allow VLC to produce more informative and smoother reward predictions than existing methods. Unlike vision language action models that predict actions in a given embodiment, VLC remains applicable on data without action labels. In future work, we would like to train video language reward models on human data. Thanks to full video conditioning, our model would also be able to represent partially observable tasks. Finally, it would be interesting to incorporate more fine-grained understanding of language, which could be enabled by ongoing advances in LLMs and VLMs. For links to the paper, source code, and more videos with reward predictions, please see our project website.